And that blackboard is what? An ideal
emitter
that emits at what? Let's assume 100%. It emits all the radiation and absorb what? All the radiation. So the blackboard emitter. And also blackboard absorber. So the radiant energy flux per unit wavelength, which is emitted by an ideal emitter at the temperature T, that's the thermodynamic temperature, within the wavelength range, lambda, to what? Lambda plus lambda. That is the wavelength, at the wavelength level, lambda. That is, at everything is about lambda. Is given by what? EB lambda. Given by EB lambda. At that wavelength, lambda. So EB lambda is given by what? Planck's law. And this is the EB lambda from quantum physics. It was found out that EB lambda is given by what? Equation 3.2. Where this is the Planck's constant, c is the speed of light in vacuum, lambda is given by wavelength, k is Boltzmann constant, c is absolute temperature. EB lambda is equal to the black body what? Monochromatic emissive power. I don't think this should be. Let's see, maybe I will check. I will check. As we go on, I will check. Okay, so let's use this. Or we can leave it for now. What? That's what I'm checking. Okay.
It is its flux per unit wavelength.
By unit
Wavelength.
yes.
Its flux like the watts per that's all. Then per unit wavelength. Wavelength is meter.
Okay, per meter cube. Okay.
We check the meter.
So the EB lambda is called the monochromatic emissive power of a black body emitter. That is monochromatic emissive power. The monochromatic power there is the lambda. Okay? At lambda, that is the emitted energy at that wavelength called lambda. So okay, heat spectra and temperature variations are illustrated with figure 3.2. So the spectra and temperature, the spectra and temperature variations of this EB lambda is illustrated. Are you seeing it? Okay. So the wavelength lambda max at the peak of EB lambda, this is EB lambda, for a given temperature, maybe for a given this temperature 1, this is another temperature, this is another temperature, and this is EB lambda, and this is what? Lambda. For any given temperature, that's what I'm trying to say. The wavelength lambda max, this is lambda max, this is lambda max, this is lambda max. The wavelength lambda max at the peak of EB lambda, at the peak of this EB lambda, for a given temperature, maybe this, is inversely proportional to temperature, and it follows the relation and follows the relationship lambda max equal to that. And I think this is Newton's law. So multiplying by this gives that. Okay, yeah. Forget about this equation yet. Forget about the equation yet. Let's make use of this. What he's trying to say here is that in figure 3.2, the wavelength, this is the wavelength, lambda, the wavelength lambda max, that's at the peak of EB lambda for a given temperature is inversely proportional to the temperature. That it says that the wavelength is inversely proportional to temperature and follows the relation. Look at it. That's lambda max T is equal to what? 2.898 times 10. So let's say this is 600 K, that's apparent temperature of the sun. Because let's say this T2, say 300 K, temperature of terrestrial bodies. That's our temperature here. What is the temperature of your body? What is the maximum temperature of your body? 36 degrees centigrade. Is that not? Okay.
36 or 37?
37 degrees centigrade. Then what is the temperature of this one now?
27 or 22.
Or what is environment? Maybe 27, 28, thereabouts. So the terrestrial body here is about that temperature, about this temperature. Okay? The temperature of the sun looks like this, and so on. This is also higher, very high. Okay, so having seen this graph, that this graph is the EB lambda versus lambda at various temperatures, and it depends on the peak of the various temperatures. So now going by this equation 3.2 and then multiplying by T to minus 5, that's to evaluate this equation. Some textbooks might not use this kind of method. They might use C1, C2, might use C1, C2, and evaluate. Then the right hand of 3.4 is a function of product lambda T only. So that means EB lambda is a function of what? A function of what?
Lambda T.
Lambda and what?
Temperature.
So that's what this equation is talking about. So you can see this equation. Then we now found out that lambda max is this due to this graph. Then multiplying that by T raised to power minus 5 gave that. And we now found out that if you multiply by T raised to power minus 5, it gives you, find out that EB lambda all over T raised to power 5 is a function of this. Or EB lambda is a function of that. So EB lambda is a function of lambda and what? That's what 3.4 is saying. So now follows that a graph of EB lambda over T raised to power 5, that's this, versus lambda T, that is this one. Forget about this unit. This unit is a kind of British unit. I would have converted it to the SI unit, but that's next time. So versus this, we collapse the graph of this into a single curve as shown in this. This collapsed so it follows that the graph of this versus this, we collapse the graph of this into a single curve as shown in figure 3.3. Eh? So this versus this versus this versus this, if you plug it, it collapsed this into this. It gave this. So the total optimum radiant energy flux. So it gave this. I think there's something I will write here. So I will fill it up now. So the total optimum radiant energy flux over all wavelengths at a temperature T is given by what? EB. I don't know what it is. So therefore, if EB lambda is dependent on lambda, that is varies with lambda temperature. That is at that lambda. Therefore, the total optimum radiant energy flux, that's over all wavelengths. That is over all wavelengths from 0 to what? Infinity. Remember, this one is for lambda. This one is at that lambda. Then this one is for all wavelengths from 0 to infinity. Is given by what? Is given by EB. So that's why it's saying that the total optimum radiant energy flux over all wavelengths at a temperature T is given by what? Where EB is given by EB the lambda. If you integrate from 0 to infinity for all wavelengths, you will now get what? EB. Okay? So it has been shown by proper integration of equation 3.5 that EB is equal to what? Sigma T4 watt per meter, so that's 3.6. Where sigma is equal to the Van Boltzmann constant, which is given by 5.6697 times 10 to the power 8 watt per meter squared per raised to the power 4. So equation 3.6 is called the Van Boltzmann law of thermal radiation. It is the particular law of thermal radiation. Just as we say that Fourier's law is a particular law. So this is a particular law of heat conduction. That is a particular law of thermal radiation. If you don't forget it, we are going to make use of it throughout. So it is a particular law of thermal. Okay, so EB is the maximum possible total radiant energy flux over all wavelengths emitted by a body at temperature what? T. It is called the emissive power of a black body emitter. Only a black body emitter can emit thermal radiation at this flux. Now, we will now define what a black body is. That's define a black body emitter. Before we define a black body emitter, let me write this. Define what is wrote here. This place should be 5, this place should be 4, and this place, let's say 3. This place should be that is dash from 0.78 dash to 25 from 0.78 to 25 microns. So let me put this one here, which is thermal unit all over hour. Where so I think here should be 5 and the 4. So this is how it looks like in our note. Okay, so definition of black body emitter. A black body emitter is one that emits radiant rays at all wavelengths. Emits the highest thermal radiation at any wavelength, at all wavelengths, at any wavelength, and over all wavelengths, and whose emissive power is a function of temperature only. No other radiator emits radiant energy more than a black body emitter. Now, we have known what a black body emitter is. Fraction. The fraction is defined as fraction of radiation flux.
So black body is like something like
Ideal. Ideal.
So from this definition now, black body radiation doesn't mean it is going to be a black stuff.
From this definition, it says black body is an ideal emitter. And an ideal emitter is an emitter that emits the highest thermal radiation